In this video, we're going to talk about some review topics, including chemical structures and how we depict structures in chemistry. And hopefully this is review for most of you, but if you need a little refresher, that's great. This will help you with that, and also you could look at your textbook as well. So the first thing I want to talk about are the condensed formulas that we'll see. And this is a very simple way to show molecules where we're showing the atoms, but we're omitting the bonds, so we won't show the bonds at all. So for example, the molecule methanol, which we'll get to understand what that name means shortly, would be CH3OH. And so we're not showing the bonds that are connecting these atoms. We're just kind of showing the atoms that are involved, and we're implying something about the connectivity here, that this carbon has these three hydrogens, and that this oxygen is also bonded to the carbon, and that this hydrogen here is bonded to that oxygen. So as we get more and more comfortable with these, they'll make a lot more sense. So another example would be something like propane here, which is CH3, CH2, CH3. So again, leaving out the bonds, but the way these are linked together sort of gives us some clues about the structure. So those are condensed formulas, and we're definitely going to see those and use those in this class. There's also Lewis structures, which many of you should have gotten to in your previous chemistry experiences. And this is now where we're going to show both the atoms and the bonds directly or explicitly. We're not going to imply them. And so you might remember how to do this, sort of this process by which we figure out how to draw Lewis structures. The first thing we have to do is count up the number of valence electrons in the structure or the compound itself, right? And so from here on out, I'm going to abbreviate electron. This is little e minus like that. Now, the way you do this, and I'm not going to go through the lengthy process here, but you use a periodic table, of course, and you identify, kind of based on the column that the element is in, how many valence electrons it brings to the party, and then add that up for all the atoms present in the molecule. So just to be clear, you're going to have to use the periodic table for this part. Or, you know, if you've gotten really good at this, you might not need to use the periodic table. So that's the first thing. Count up those total number of valence electrons in the molecule. Again, valence electrons, not total electrons. If the compound has a negative charge, right, so that means it's negative because it has an extra electron or two or three or however many, you're going to add that charge, those numbers of electrons, to your total. But if it has a positive charge, it's positive because it's deficient somewhat in electrons, and so you're going to subtract those electrons from your total, not to your total. Then you're going to distribute those valence electrons as bonds to start with. So you'll put one bond between each of the connected atoms. And then starting at the, what we'll say, outside, so the outer atoms, add lone pairs so that each atom obeys the octet rule or the duet rule, as we'll see for hydrogen. And if you run out of valence electrons from your total that you've added up, then it's time to start making double bonds. Okay. So then there are a few error checking things we should do. Make sure that your total number of electrons, the sum equals this total number of electrons. So count those lone pairs, count the bonds, make sure that that kind of goes back to your previous number that you've calculated. Also make sure that the octet rule is obeyed, and that means that each atom is surrounded by 8 total electrons, or 2 electrons for the case of hydrogen here. And so as you get more and more comfortable with these, you'll realize that certain atoms tend very often to make a certain number of covalent bonds. So for example, carbon tends to make 4 bonds. Nitrogen tends to make 3, but we're going to see, and you may have encountered this, sometimes 4. Never 5 for carbon and nitrogen. And for our purposes, carbon's always going to be 4, nitrogen's going to be 3 or 4. Hydrogen is almost always going to make 1 bond. We could argue sometimes 0, but we'll talk about that later on in the course. And then oxygen typically will make 2 bonds, but as we'll see soon, sometimes just 1 bond. So kind of keep those in mind a little bit as we're going through these. So let's do a couple examples. First up would be draw the Lewis structure of each of these molecules shown. We're going to start with oxygen, molecular oxygen, O2. And so what I'll do is I'll kind of make a little mini table. I'll say what atom or atoms are present in the molecule. Well, it's just the oxygen, so O. And then we'll ask how many valence electrons are present. And again, this is where you'd go to the periodic table. We'll see that oxygen brings 6 valence electrons to the party. Now, we'll multiply that by the 2 that we have, and so we see we have 12 electrons total in this molecule. There's no charge on O2, it's not negative or positive, so 12 is the number we're going to go with. So, you know, we got a step-by-step process that you can go through for this. On the previous page, I'm just going to kind of show you the answers for these. What you'll discover is that oxygen is going to make a double bond to another oxygen atom, and then we're going to have some lone pairs left over, like this. And now, just to be sure and to make sure, you know, we've have the right numbers, I'm going to count the number of electrons. So each bond is 2, and each lone pair is 2. So I've got 1, 2, 3, 4, 5, 6 pairs, which means 12 total electrons. So based on that, we're in good shape with that structure. Again, I'm keeping this a little bit, you know, on the quick side because this is hopefully review for you. But if you need more help with this, please, you know, look at the book, read the notes, come see me, etc. Okay, let's look at bicarbonate now. So CO3 with a negative charge. Notice it's got a negative charge right there. I'm going to follow a simple or a similar procedure where I think about what atoms I have. Here I've got a carbon, an oxygen, and a hydrogen. And then we're going to think about how many valence electrons each of those brings to the party. Carbon brings 4. Oxygen, again, brings 6. And hydrogen only brings 1. And now we got to look at that structure here, or the formula, and say, well, how many of each is there going to be? Well, there's only one carbon, and there are, however, 3 oxygens. So I'm going to do times 3, and then we'll kind of go through and sum those up. So I've got 4 from carbon, 18 from the oxygens, and 1 from the hydrogen. And so if we sum those up, we get 23 electrons. But remember, we have this negative charge here, so we need to add 1, and so we have 24 electrons is the total number of valence electrons in this molecule. And so again, for these, especially when these polyatomic ions like this, when you see you've got multiple oxygens, chances are your carbon is going to be in the center here, and you're going to have your 3 oxygens kind of spread out like that. And you'll quickly discover in doing the math here that you're going to have a double bond going to one of those, and you're going to need a hydrogen going to one of the other oxygens like that. And then the rest of those electrons are going to be in the form of lone pairs. So we're going to have lone pairs on that oxygen. We're going to have more lone pairs on this one, and lone pairs here and here. And this oxygen right here has a lot of electrons around it. It's only making 1 bond. When oxygen's only making 1 bond, it carries a negative charge. So that's where that negative charge comes from there. So again, check yourself. You know, if you add up the total number of electrons, valence electrons here, it's going to equal 24. And also, everything, all atoms should have satisfied octets. If you look at the carbon and the 3 oxygens, there are 8 electrons surrounding each of those. And then the hydrogen has a satisfied duet, having 2 electrons in that bond. So you go through and check, yep, this is the correct structure for bicarbonate. Let's do one more. We'll do methanol, shown right here. So methanol, same idea here, atom, I've got C's, O's, H's, like that. Valence electrons, carbon's going to bring 4, oxygen's going to bring 6, and hydrogen will bring 1. We only have 1 carbon, so that's going to be 4. We only have 1 oxygen. That'll bring 6 electrons, but we do have 4 hydrogens, and therefore that's going to be 4. No charges on methanol here. It's a neutral molecule, and so we sum these up and we get 14 electrons like that. Similarly as before, you know, carbon tends to be a central molecule, especially when we get into this more organic-y type molecule like this. And what we'll see is the connectivity here. It's kind of, there's a clue kind of in the structure here that this oxygen is going to have to be bonded to that carbon. You know, these hydrogens can't make more than 1 bond. So we're going to have the oxygen bonded to the carbon. And there's also a clue here in the structure that this hydrogen is bonded to the oxygen, right? So we're going to draw that. And really, it's kind of filling in the rest of this. Well, we've got those other 3 hydrogens, which are going to be bonded to the carbon. Well, and then each of those hydrogens that I've drawn, all 4 of them, in fact, have satisfied duets. The central carbon here has satisfied its octet with those 4 bonds to hydrogen. But notice the oxygen's making the 2 bonds, so it's 4 electrons, so it's going to need some additional electrons. And as we'll see, that's in the form of 2 lone pairs. So again, you add all of those up, you'll discover that we've got 14 electrons total, and that one checks out. Okay, the next one I want to show you is the line angle notation, sometimes called a skeletal formula. And this is like sort of the most simplistic of all. It's very easy to see. And we use this a lot when we start getting into bigger molecules, because it sometimes gets a little bit challenging in organic chemistry and biochemistry to show these big old molecules if we were to show them as we would like a Lewis structure up here with all those bonds drawn out and all the carbons and the hydrogens. So what we do in line angle notation is that the carbons and the hydrogens that are attached to the carbons are replaced with just lines. We're going to still show oxygens and nitrogens and fluorines and chlorines and everything else. We're going to write out the symbol. And any hydrogens that are attached to those types of atoms we're going to show as well. So the big hint here is that carbon atoms are at endpoints, elbows, and intersections. So you're going to hear me say that quite a bit. So just as an example, we'll draw some line angle structures for these. So first of all, this is propane. We showed this previously for the condensed formula, of course. So propane here has 3 total carbons, right? 1, 2, 3. And we're going to simplify that structure down so much that we're just going to show lines. And so the way propane looks in line angle notation is like this, seriously. What's going on here? So remember what we said, that the carbons are at the endpoints, elbows, and intersections. Well, we have some endpoints. There's an endpoint here, and there's an endpoint there. So those are each carbons, and in fact, they're the 2 carbons at the end of propane. So we're not going to show the C or the H's that are bonded there. We're just going to assume that they're there. And then we also have an elbow right there, right? So that elbow also is a carbon, and it has 2 hydrogens bonded to it, as it's shown in the condensed formula. So this is a really, really simple way to show that. And in fact, now I should point out that the line itself is the bond, right? So that's a bond, and as is this part of the line here. Right, the line is the bond between this carbon here and this carbon here and that carbon there. So get used to seeing these types of structures. So if it's just carbons and hydrogens, all you would see would be lines like that. But certainly there are many more complicated molecules in biochemistry. And so, for example, methanol now has this OH in it, and we cannot simplify away the oxygen and the hydrogen attached to it. We do have to show this OH in line angle notation. So the line angle structure for methanol is this. Oh, wrong color. Seriously, just has a line there. And again, same idea. Now we've got an endpoint here. The end of that line is a carbon. So we are implying that there's a carbon right here with the 3 hydrogens attached to it. And then we still show explicitly the OH right there. So I want to write that down. We must show the O and H's, I guess it's just one H attached to it. And now this is true whether it's an oxygen or, as I say up here, it could also, if it's a nitrogen, right? So I need to show the nitrogen, I need to show the oxygen, and any hydrogens that are attached to those nitrogens or oxygens or other things like sulfurs and things like that, which we'll get into later on. So that's a little bit more complicated molecule. It's got some other atoms in it. Let's look at another one that's maybe just even a little bit more complicated. This is acetone. So look carefully at what the structure is saying. I've got a CH3 on each end, and then in the middle, I've got a CO. Now, if I told you to draw the Lewis structure and you counted up all the valence electrons and all that sort of stuff, you would discover that acetone has a structure like this, where there's a carbon-oxygen double bond, and then you would discover that the those CH3s are like this. So that's not a line angle structure, that's the Lewis structure. So what we want to convert that is into this line angle structure, which would very simply just look like this, right? Have the double bond like this, and I would just draw then the lines where those carbons are. And I should be very clear to draw all of the lone pairs in here as well. So this is the line angle structure for acetone. And one thing I want to point out is that there's an intersection right there. And then we've got, again, endpoints where our other carbons are. We got endpoint there, and then on the other end to the left. So again, just to kind of look at the structure, right? This central carbon is now an intersection, and so we're implying that it's there. And then these methyl groups, as we'll learn to call them, these CH3 groups here, are on the ends. But it's simplified in this much easier to see and draw form shown there.